Why does machine learning love more data? Here are 5 data points from an online store's customer spending and a question mark next to them. Compute the average of those 5 and you get 63 euros. Draw a different 5 from the very same store and the average swings to 19 euros. Same population, wildly different answers. Now look at thousands of data points instead of 5, the cloud titans. The average settles near 41 euros and barely moves. More data doesn't just give you more numbers, it gives you steadier answers. That steadiness has a name, and by the end of this chapter you will know exactly why it happens and when it doesn't. Picture 5 customers at an online store. They spend 12 euros, 80 euros, 5 euros, 200 euros, and 18 euros. One customer spends far more than the rest, a single outlier sitting in a tiny sample. The sample mean is just the sum of your observations divided by how many there are. X bar equals x1 plus x2 and so on divided by n. Add these 5 and divide by 5. 12 plus 80 plus 5 plus 200 plus 18 over 5 equals 63 euros. Drop that one outlier and the mean falls all the way to 29 euros. With only 5 data points, every single value has an outsized vote in the final answer. Take a fair coin, flip it once, you might get heads, might get tails. The running proportion of heads bounces around wildly. After 10 flips, the proportion might sit far from 50%. After 100 flips, it wanders closer but still swings. After 10,000 flips, the running proportion settles in tight around 0.5, the coin's true probability of heads. This is the law of large numbers. As the sample size n grows toward infinity, the sample mean x bar converges to the true expected value E of x. It doesn't matter whether x is a coin flip or a customer's spending. Enough repetitions and the average finds the truth. Back to our online store. At n equals 5, the sample mean was 63 euros, an outlier-driven guess. At n equals 500, it settles to 45 euros. At n equals 50,000, it lands at 41.2 euros, barely moving from there. It's worth separating two ideas that sound alike. The expected value E of x is the true, fixed, usually unknown quantity we are trying to learn. The sample mean x bar is what we actually compute from the data we happen to collect. Same story with delivery times. The true average delivery time is 30 minutes. A sample of 10 deliveries might show 37 minutes, a rough guess. A sample of 10,000 deliveries shows 30.4 minutes, remarkably close to the truth. With enough data, the sample mean becomes a reliable stand-in for the expected value you can never directly observe. Customer spending itself is not bell-shaped, it's skewed, with most customers spending modestly and a long tail of big spenders. But watch what happens if we repeat the sampling process. Draw a sample of 30 customers, compute its mean. Draw another sample of 30, compute its mean. Do this hundreds of times and plot every mean we get. Those means pile up into a bell curve, even though the data they came from was never normal to begin with. This is the central limit theorem. The sample mean x bar is approximately normally distributed with mean mu and variance sigma squared over n. It's one of the most surprising facts in statistics. Averaging tames almost any kind of randomness into a predictable bell-shaped spread. That bell curve has a width, and the width has a name, the standard error, sigma divided by the square root of n. It tells us how much a sample mean typically wanders from the true mean. At n equals 100, the standard error is fairly wide. At n equals 10,000, it's noticeably tighter. At n equals 1 million, it's tighter still. But look closely at the numbers. Going from 100 to 10,000 data points, a 100-fold increase, only shrinks the standard error by a factor of 10. That's the square root law at work. Precision improves with more data, but with diminishing returns. Doubling your precision means quadrupling your data, not doubling it. This idea threads through machine learning everywhere. Model training learns the underlying pattern, not the noise in any one batch, because gradients themselves are averages. Model evaluation needs a real sample size. 20 test examples versus 20,000 gives very different confidence in a reported accuracy. A B testing leans on exactly this math to decide whether a difference between two groups is a real effect or just random noise. Recommendation systems average many ratings, so one furious or one delighted reviewer doesn't hijack the score. Medical machine learning needs large representative trials before trusting an estimated treatment effect, and sensor data gets averaged constantly, letting many noisy readings cancel out into one trustworthy number. 6 different jobs, one underlying idea, averages stabilize, and we can predict how fast. Here's the catch. Imagine 2 million data points, but they're a biased sample. An arrow points from that huge cloud straight past the true answer. More data doesn't fix bias, it just makes you confidently, precisely wrong. Duplicated records, skewed collection methods, low quality labels, pile those up at scale, and you still get a bad estimate, just one that looks impressively certain. So here's where this chapter lands. The law of large numbers explains why averages settle down as data grows. The central limit theorem explains that their spread shrinks in a predictable bell-shaped way. Put together, they explain why machine learning depends on data quantity and quality and representativeness, all three together. Next, we move into part 2, learning from data. Part 2 will unfold as a focused 8-video series, taking us from these statistical foundations into the mechanics of learning from examples. Thank you for watching. If this made the law of large numbers and the central limit theorem click, subscribe for the rest of the statistics for machine learning series. Stay curious. Keep exploring statistics.